Today's speaker, Daniel Agterberg, from University of Wisconsin-Milwaukee. Daniel did his PhD at the University of Toronto, and then he was a postdoc at ETH in Zurich, and after that a natural hydrokinetic field lab in Tallahassee. And now he is an associate professor, a full professor at University of Wisconsin-Milwaukee. Thank you very much for coming.
Well, thank you for having me. I thank all the organizers for organizing this. It's a great idea to have two communities mixed together like this. I've already learned a lot by having this, and Stockholm's also a beautiful town, so I'm really enjoying this. So I'll be talking about FFLO superconductors, which many of you are familiar with, and also pair density wave, which is just a slight generalization of this. And in fact, it turns out that a lot of what I talk about has strong overlaps with what Vincent Liu talked about in a great deal of his talk. In fact, I'll be showing some of the same experimental results. All right, so this is work done in collaboration with Manfred Siegrist in Zurich and Hiro Tsunosugu at the ISST at the University of Tokyo, and then 3 graduate students, Ravinder Kaur, Shantanu Mukherjee, and Xichao Zhang at the University of Wisconsin-Milwaukee. And so what I'll go over is just why do I want to look at these pair density wave phases. Maybe this audience doesn't need such a justification, but never hurts. And then after that, I'm going to turn temporarily to a microscopic model for the creation of spatially oscillating superconducting states in superconductors without parity symmetry. And I thought I would do that here because I think maybe people in the cold atom community might benefit from seeing another way of making something like an FFLO state, but in a very different context. And then after that, I'll talk about the Ginzburg-Landau-Wilson theories of pair density wave phases, in particular trying to classify what kind of ground states can happen, what are the topological line defects, and then the fluctuation physics, in particular in 2 dimensions, which I'll go over relatively quickly. And so what's interesting is that you'll get some novel topological defects, and that drives very interesting new types of phases in 2 dimensions in these FFLO and pair density wave states. All right, so what do I mean by pair density wave? I simply mean superconducting order parameters that oscillate in space. And so this is the simplest example. And as I've mentioned before, the Fuller-Farrell-Larkin-Chinnikov state is a specific example. And in this case, the spatial oscillations on the order of the coherence length of the superconducting state. I'll be interested in situations where these spatial oscillations are on the order of microscopic length scales as well as on the order of the coherence length in the superconducting state. And then yesterday we heard Vincent Liu give a nice talk about finite momentum Bose-Einstein condensates and supersolids. And so a lot of what I'll be talking about is actually closely related to that. All right, so here's the standard example. I know many of you are familiar with this, but if you look at a spin singlet pairing in a Zeeman field, there's a couple points I want to make on this slide. Okay, let me just start here. So this is your usual Fermi surface. So imagining that we're in the weak coupling limit, and so that the Fermi surface is very important. Then we usually pair states k up with minus k down, etc. Then if we apply a Zeeman field, you all know that you split the surface into spin down and spin up surfaces. And then you can no longer pair states up and down easily unless you have this finite momentum Q. Right. So here if I pair this state here, I want to pair it with this state on the other surface, but that's not a minus k, it's at minus k plus Q. And the point I want to make here, and in fact this point was made in this paper by one of our organizers, who was a co-author in this, is that in other than 1 dimension, you don't have many states for which you can use the same Q vector. So in particular, if I want to use this Q vector to pair these states, I do a terrible job because I gain a lot of kinetic energy because these excitations are not on the Fermi surface anymore. And so you only pair a lot of states transverse to this Q direction, and then you lose a lot of condensation energy from the rest of the Fermi surface. So when I talk about these broken inversion materials, the situation is going to be very different. In 2 dimensions, you'll have a lot of condensation energy by creating these finite momentum states. And here's a picture from this review article, Matsuda Shimahara, where you see, this is for 2 dimensions, it's a weak coupling theory, and you have a cascade of phase transitions. So down here, this is field versus temperature, here you have a uniform state, and as you go down you get this Larkin and Chinnikov state where the oscillations are one-dimensional, but then you get this 3Q phase, which they call triangular, and you get this square and this hexagonal as you increase field. Alright, so this is cascade of FFLO states, and that'll be of interest later on when we're trying to classify the possible types of order parameters you get in this case.
Excuse me, can I ask a question here?
Yeah.
So I understand that these are some possible mean fields, right, for the order parameters. So you can pick up, consider different types of trial functions.
Yes.
So when you build this phase diagram, is there a statement that these are all possible mean fields that you've considered?
These are all these are the ground states of a two-dimensional cylindrical Fermi surface in the Zeeman field. So these are the low energy. These are the mean field solutions for that. So these are the mean field solutions.
So Daniel, one more thing. What's the difference between hexagonal and triangular?
I'll show you later. There is a
Same
difference.
thing.
Well, okay. This, in the simplest representation, involves 3 Q vectors. This involves 6 Q vectors. So, and I'll explain that later.
Is it distorted?
Sorry?
Is it distorted now? Okay.
Well,
all
okay.
right. Never mind.
So, in some sense, not distorted. So this is triangle, and then hexagonal has those Q vectors involved. And so as you go down, you just pick up more and more Q vectors. Right. Anyhow, so this is a mean field result in 2 dimensions. And so, of course, has to be seriously considered in the presence of fluctuations. But these are all stable phases. All right, so I've already mentioned this point here. And then very early on, in the early days, when it was first discovered, there were 2 possibilities listed right away. The first was by Fulda and Farrell, where they considered a single plane wave oscillating like this. And the second possibility was this cosine QR dependence, which is that of Larkin and Chinnikov. And then in most cases, it's this phase that's the most relevant, right? We typically see the Larkin and Chinnikov. Two Q modes, and then in general, you can introduce higher order Q modes, but the symmetries are well represented by this state here. All right, so why are we interested from a materials point of view? Well, the answer is there's a variety of materials for which these phases are relevant. And I'll just go over some of them here. One is cerium, cobalt, indium 5. Now, the situation isn't so clear-cut. People used to think this was a Fulda, Farrell, Larkin, and Chinnikov phase up here. So this is field. I see that axis has been cut off versus temperature. And in this low temperature, high field region, what people saw with thermodynamic measurements is they saw a second-order phase transition here and a first-order phase transition. And because the upper critical field is sufficiently high, and because this is quasi-two-dimensional, people really did believe this was a Fulda, Farrell, Larkin, and Chinnikov phase for many years. Recently, there has been evidence of a spin density wave order showing up in this phase as well. And so it's been proposed that this is not just a natural Fulda, Farrell, Larkin, and Chinnikov phase, but it's a combination of a more general pair-density wave order, which oscillates on a length scale which is much smaller than the coherence length, combined with the D-wave superconductor. So I'm not going to go into that, but nevertheless, there is some pair-density wave order showing up in this phase in either interpretation of that. And then one of the things I forgot to mention on the previous slide is the easiest way to get some indication for these Fulda, Farrell, Larkin, and Chinnikov phases is to see an upturn in the critical field at low temperatures. So that's the simplest experiments that would tell you it exists. And then there are a series of materials that show this behavior. And so here is a broken inversion material, cerium, rhodium, silicon 3, and that shows this very strong upturn in the critical field for various field orientations. And so that shows some evidence of these phases. And then there's organic superconductors. These are some resistivity measurements, so not the perfect measurement to measure a phase diagram, but nevertheless, the interpretation of the data. So this is a quasi-one-dimensional organic superconductor, and the interpretation of the data is that this up here is a Fulda, Farrell, Larkin, and Chinnikov phase. And then there's a quasi-two-dimensional organic superconductor, where, again, a few phase transitions have been seen through thermodynamic measurements, specific heat in particular. So they've seen a second-order transition, a first-order transition, and then there have been arguments that as this goes further down in temperature, this Fulda, Farrell, Larkin, and Chinnikov phase widens out, and so it takes up more of the phase diagram over there.
So the magnetic field is in plane, right?
Yes, it's in plane, yes, in both cases. And even in the cerium, cobalt, indium 5.
So this H parallel C star, that's the inset shows H parallel.
Yeah, these are much lower fields. So it's just showing the difference in the critical fields for different directions. All right. And so what interested me to really start thinking about these was there were a series of proposals for zero field pair-density wave states. So what we're used to is having pair-density wave phases induced by a magnetic field. But there's also the possibility of having these in zero magnetic fields. And this was actually originally from a combined theory experiment paper. They suggested that in this lanthanum barium copper oxide, a high TC superconductor near 1/8 filling, that it was possible that there was a pair density wave state. And this came from a detailed analysis of the C-axis resistivity, where they noticed that the system looked very uncoupled in the C-axis, but strongly coupled in the plane. And the way they could interpret that was, and I'm glossing over some of the details here, I can tell you more about it later, but the way they could interpret that was that the layers decoupled because you had a pair density wave order in individual layers. So to make that clear, this material is a single layer, has orthorhombic symmetry, so it goes along a particular direction, but as you change layers, that direction rotates by 90 degrees. And so if you have a pair density wave in a single layer, you have one above it is rotated by 90 degrees, and so you don't have C-axis coupling because of that. If you had a regular order parameter, you would get C-axis coupling along the C-axis. And so it was suggested that in this material here, 1/8 filling, you do have such a phase. And then there was also some numerical support from this, from numerical studies of the TJ model by Ogata's group at the University of Tokyo, where here you can see the order parameters spatially varying. Well, this is with 12 lattice spacings, and the proposals have been with 8 lattice spacings. But these phases have been found in microscopic models at the mean field level. And then yesterday, we heard Vincent Liu talk about some very nice Bose-Einstein constant measurements where on the p-band in an optical lattice, and I'm not going to go through the details, but there the momentum distribution shows 2 peaks as opposed to a peak at q equals 0, suggesting again that this is a finite momentum condensate where the oscillations are on the order of a lattice spacing. And then if you go even a little bit further back to the 1990s, there were a couple proposals of in 2-dimensional helium-4 where it was suggested that the number of the density of vortices is very high, and the densities of vortices is very high, then you might get, instead of a vortex liquid phase, you might actually get a vortex anti-vortex lattice. And so Suchin Zhang considered that, and then Gabai and Kapitolnik also considered this possibility. And that's an example of the pair density wave state as well. All right, and then very recently, there have been some studies where you look at unconventional superconductors in finite dimensions, and then because of the edges of the system are pair breaking, you find that the natural solutions that come out of these restricted regions are oscillating, spatially oscillating states. And so there's a variety of reasons to consider these phases in zero magnetic field. All right. So that was my motivation. And now I want to turn to this microscopic theory of how you can develop a pair density wave phase in superconductors without parity symmetry. So here, again, is some motivation for materials that break parity symmetry. The most commonly studied is the cerium platinum 3 silicon. And what's important here is the crystal structure. And so if you notice, if I imagine doing a mirror plane reflection through here, you can see that this atom has no counterpart down here. And so the reflection symmetry along the C-axis doesn't exist in this material. And that's true for a variety of materials, all 3 of these. And then what was very interesting when it was first discovered was that their critical fields were exceptionally high. And so people thought that these would be triplet superconductors. But it turns out that the broken inversion symmetry can actually explain the high critical field for a singlet superconductor, but I'm not going to go into that here. So there's some materials for which this applies. And then also more recently, in 2007, and then even from 2004, if you look at the interface of lanthanum aluminate and strontium titanate in this region here, you find that you get a 2-dimensional electron gas. It's believed to be a 2-dimensional electron gas, and here's a picture of it. So both of these are insulators, and so the interface would be metallic. And then you can apply an electric field perpendicular to the normal of this, and in that case then, if this system is superconducting, which it was found to be in 2007 by Joachim Mannert's group, that would be a broken inversion superconductor as well. And so these ideas would apply to these 2-dimensional metallic gases. All right. So I'm not going to go spend too much time on all the results you get for non-centrosymmetric superconductors. I'm going to focus in particular on the case where you have this paradensity wave state, but I thought it'd be useful just to see how you can describe these theoretically. So here I have the usual kinetic energy term, and here I have a pairing term, and so this is just weak coupling. The only thing that changes when you break inversion symmetry is you add this so-called asymmetric spin orbit coupling term. And that's what I've written here. And so this is the spin of a quasi-particle, and this is just some vector g. And if you impose, and this is some coefficient alpha, so the only operator here is the spin. And so if you impose that this Hamiltonian is time reversal invariant, then under time reversal, both spin and k change sign, and that means that this vector g must be odd. All right, so imposing time reversal invariance guarantees that if I change the sign of k, then the vector g must change sign. Now, if you also impose parity symmetry, then you find that g of k must equal g of minus k. And so that means that this term cannot exist when parity symmetry is present. So this term explicitly breaks parity symmetry. Right? And so you can imagine this like a k-dependent Zeeman field, because this is just the spin operator showing here, and then the single particle excitations have their spins polarized parallel and anti-parallel to this vector g. All right. So for the materials of interest, you can get an estimate of how big this vector g is. Also, yeah, so let me just make one point here which will become relevant later. So you naturally get two bands of different spin species coming from this because of this vector g of k.
Excuse me, how many bands do the materials actually have, apart from the spin splitting?
How many bands?
Yes.
They have many bands, typically. I mean, here's a picture. So this is two of the bands that are relevant for the physics near the Fermi surface.
So, but the model you showed had just spin split bands, right? And no
Yeah, but so the spin split applies to each of the bands as this picture shows. So here you have yellow and green Fermi surfaces. Yellow is for one spin orientation, green is for the other.
So, and the interaction should be diagonal in the band index. So, because the interactions, basically, you're saying that the models decouple for different bands.
Yeah, I mean, you can describe each one of these bands by that interaction. So it's not going to really matter a lot, actually. I mean, you raise a valid point that you can have a Hamiltonian that has band indices in addition to the spin indices, but it's not going to matter too much for my discussion. All right. So the only point I want to make here is that band structure calculations, in this you can see the difference between the two spin split bands between the yellow and green. And because you can see the difference, this tells you that the coupling for the spin orbit coupling is much, much larger than the pairing energy. And so for considering superconducting pairing, you have to consider yourself in the strong spin split limit, in particular for this material. And so that changes the physics quite a bit. All right, so how does that change the physics? And this is really the central slide. So here, I'm looking at what happens when you have these this asymmetric spin orbit coupling. So here's your usual two-dimensional Fermi gas with no asymmetric spin orbit coupling. Then you add this spin orbit coupling term, and you split the spin states, and the spin states are running tangential to each of the bands here. And then on top of that, you add a magnetic field. But what a magnetic field does, and this is important, is it takes the center of each of these surfaces and shifts them in opposite directions. And so you see this band shifts down, and this band shifts up. And so then when you want to think about pairing in the states, then you find that instead of pairing through the original center of the Brillouin zone, it makes more sense to pair through the shifted center of each of these bands. And so for this Fermi surface here, you would pair through, this would be the original kx equals ky equals 0. So for this Fermi surface here, you'd pair around this band, and the other band would prefer to pair through the center, through the opposite Q vector. So this is one Q vector, and that's the other one here. And so now you can see there's a natural mechanism to get, in 2 dimensions, to take advantage of many states, if this in particular, this is a cylindrical band, to create a finite momentum pairing state. All right, and so just to convince you, I mean, this is a central feature is that the band center has to shift. It's actually a little bit of simple algebra to see that, and that's what I've done here, to show you that indeed the centers do shift. So here's a dispersion relationship with this asymmetric spin orbit coupling and a Zeeman field. Now I've already told you that I'm going to take this to be a large energy scale, so this is going to be a small energy scale, so I can expand in terms of this divided by that. And when you do that, you get this plus or minus b dot g hat of k. And I told you on the previous slide that g of k is odd in k, and the lowest order power that shows up is linear in k. All right, and so in particular, you get a term that's linear in ky for the field along the x direction. And so automatically, if you have a term linear in your dispersion, you can compensate that by shifting the center, right? And so that's where this comes from, and the plus or minus tells you that the two bands shift in opposite directions.
Daniel?
Yeah.
So just try to figure out the picture. So which direction is Q in the last one? In the vertical.
Q is the shift between this center here and this here. So this is Q. Right? From the center to here.
So basically still parry the particle from the respective Fermi surface.
Yeah, but through the shifted center.
And then the field is in the.
Yeah, the field is in the x direction, the q is in the y direction. Bx, ky, so you shift the surfaces up and down in the y direction. All right. And so then naturally, you pick up this finite central mass pairing state from this.
So in this case, it's still similar to the LO or FF case. You only
This is like the FF case.
use part of the Fermi surface, not all the particle, not all the quarter particle will contribute to the condensation energy.
Yeah, I mean, so the difference is that instead of using a small region of each Fermi surface, you can use an entire band to parallel.
How does it work? Dude, that's the exact point I try to figure out. Because in the FFO case, it's like you separate, you relatively shift the two balls, right?
Yeah.
And only you pair around like the cross-section area. The cross-section area, so the particle stays in the cross-section area would contribute to the condensation energy, right? So.
Yeah, so instead of pairing k and minus k, which would I pair through 0, I now pair k plus q and minus k plus q. And because the center is shifted, I can pair every state on this band.
But your K is not along B.
K is not along.
Sorry, Q.
Q is not along. Yeah, that's different. Q is not along B.
So it's
Yeah,
orthogonal. That's different from.
that's different. That's true. And so in cubic materials, of some particular cubic materials, if you have O symmetry, then you can find that your K is along B in that case. But it takes a different type of spin-orbit coupling to do that.
But you want to pair the particle between two different Fermi surfaces? Or
Oh,
the same Fermi
look,
surfaces?
so here, you can see because of the asymmetric spin-orbit coupling, the spins are largely already anti-parallel on each band like this.
Oh, I see. So it's
Yeah.
on the same Fermi surface.
Ah, okay, yeah, so this
Now
is the
we got
point
a
I didn't
point,
emphasize.
okay.
Yeah, so they're pairing on the same band, opposite spins.
Very good, yeah.
All right. So this is a picture for how you can come up with this kind of state. And of course, you can do a much better job with such a calculation, but it gives you the qualitative physics right away. And in fact, you can then turn to a full solution of the Eilenberger equations for this. This is just a very good way of doing weak coupling theories. And you can ask, what are the phase diagrams? And you find that there's a variety of possible phase diagrams depending on the relative density of states of each of these bands. And so the two density of states are equal. You find that you get three phases, a uniform phase, very much like the FFLO case, actually. I mean, it survives some much higher temperatures. But then you get a small region of this helical phase, which just means a single Q modulation. And then you also get this multiple Q phase where you get both Qs modulating. You get e to the IQ and e to the minus IQ, and then you get higher order Qs as well.
So what do you mean by uniform phase? There are vortices there, right?
This is a two-dimensional system of the field in plane, and so there are no vortices in that particular case there. Yeah, so this is, and then, yeah, so then you could add vortices to this picture as well.
What is the spin structure of this thing? Because it's very non-trivial. It should be, delta should be a spin tensor in the spin space, right? So spin is not a good quantum number anyways.
Yeah, that's right.
So what is the spin symmetry of the pair?
Of the Cooper pair, you mix spin singlet and triplet generically. And it's actually, okay, maybe this takes me a little bit aside, but so you can define two gaps, one which pairs these two, and then one which, say, pairs these two. And those can be uniform in momentum. But then, if those gaps are equal magnitude, then you either have a singlet or triplet pure state. If they have different magnitudes, you have a mixture of singlet and triplet.
So without magnetic field, you have time reversal symmetry, right? Present.
Yeah, that's
so
right.
When you build your Cooper pairs, are they basically time reversal partners to each other, or no?
Without magnetic field, they're time reversal partners of each other. Yes. And you can see that because K spin this way, the time reversal partner is minus k spin the opposite way.
Oh, okay.
If you put on the same parameters, don't you get P wave? P plus IP or something?
No, this is, it's not P wave.
That's
This
no
is,
way.
But you got a symmetric state as a function of K, right? Because
okay. This was the source of some confusion in the beginning of this field. This is an S-wave order parameter. If you take the limits, as you take the two bands on top of each other, you'll get an S-wave state. But then if I take the gaps to be opposite sign, this will be an S-wave. If I take the gaps to be the same sign, then I will get a P-wave contribution. So it's a mixture of singlet and triplet. It's a mixture of S-wave and P-wave. Because the system actually breaks parity symmetry, you don't have this natural classification. But there is a well-defined singlet limit and a well-defined triplet limit, and now they belong to the same symmetry class, and so you can admix them.
So Daniel, you probably want to, for your interaction, the coupling has to be weaker compared with the band gap, right? Otherwise, you're going to mix all of
With the splitting, yes.
Splitting. That's given
Yeah.
by G, I guess.
Yes, then alpha, this
Alpha.
coefficient alpha, yeah. So in the materials of interest, it typically is. So the spin orbit coupling is on the order of 100 MeV, and then gaps are in the order of maybe 1 or 2 MeV. So it's really a large
That's
energy.
good.
All right. So back to this phase diagram now. So if you then allow the bands to be, so this is when the two split bands have the same densities of states. If you now allow the density of states between these two bands to be slightly different, which in principle they would be, and in heavy fermion superconductors they can be dramatically different, then you find the phase diagram is different. You get this helical phase throughout most of the phase diagram, and then only in a small region here you get this multiple Q phase. All right, and so that was a microscopic argument, but of course the nice thing about this helical phase is that there's also a macroscopic argument that shows its existence. So this is not true for the Fuller-Larkin and Chinnikov phase. Well, it is true in some sense for that, but you have to, in that case, you have to change the sign of this coefficient of the mass to generate the FFLO state. But in this case here, because you break parity symmetry, it turns out that you have a new term that's allowed in your Ginzburg-Landau free energy. And that's a Lifshitz invariant and has this form here. Just to make this simpler, I've made this look like, this is the surface normal, so this would be along the z-axis. This is the magnetic field, and then this is, without the vector potential present, this is the uniform current that you would get in usual Ginzburg-Landau free energy. And so you get this coupling between B and this uniform current, and so once you have a term that's linear in the gradient, then you can minimize the total free energy. And because it's linear in gradient, the gradient has to become non-zero. It's a standard feature of Lifshitz invariance, and so you naturally get this phase coming out. And then also, from the form of this coupling, you find that the Q vector must be perpendicular to the magnetic field as well. And so you can understand this from a macroscopic argument why these phases appear as well. And I want to make a comment that even though this has the structure of a current carrying phase in a superconductor, this state actually carries no current. And that just simply follows because when you minimize the total free energy, you're satisfying the requirement that the derivative with respect to Q must be zero. But Q is related to the vector potential A, Q minus EA. And so that's telling you that the derivative of the vector potential is zero, and so therefore the state carries no current.
So normally the current density operator is like a I delta with some kind of minus sign between two terms, right? This is different.
Oh, sorry, I used to have, yeah, you're right, you're absolutely right. There should be a minus sign here. I changed notation from D to vector to gradient, and then I had no minus sign in the, you're right, you're absolutely right. I meant to put an I in here when I changed this. So trying to make it look simpler, I didn't make it look simpler, I made it look wrong. That's okay. Yes, but, I mean, nevertheless, the same arguments still apply. All right, so that's all I wanted to say about this helical phase in non-centrosymmetric materials. And so it might be interesting to know if in the cold atom community, if there is a way of generating some sort of Rashba-like spin-orbit interaction, and to see if there is a way then, and then if you can generate that, then to rotate the system in, I don't know if this is going to work at all, but if you can have some fictitious field that can generate the kind of bands necessary for that, then maybe there's a way of constructing these states in a robust way.
So I think you should discuss with Jonas Larsson, who's a local I mean, currently a force garage is tending the neighboring building. I mean, he's hanging around, not here right now, I think, but I mean, he's usually here. I mean, he knows about these ways of creating these rust couplings in cold atoms.
Okay.
So I mean, you might be interested to discuss with him. I mean, he's not here right now, but I mean, probably he gets a talk on Monday. I'm not sure how.
I'm here, so
Yeah.
I'll look for him then. Okay, thanks. All right, so that's all I want to say about this microscopic pairing mechanism. And I want to talk about symmetry-based theories of these pair density wave spaces. All right, so going back to original motivation, there's a series of general questions you can ask. So here I'm back to this picture that I showed you before, and you can see in this two-dimensional picture you get a variety of phases, and the properties of these phases are actually quite different. So in particular in this phase here, the gap vanishes along lines in real space, but in this phase here it vanishes along points in real space, and the FFLO doesn't vanish anywhere in real space. And so they're qualitatively different phases. And it'd be interesting to ask, what kind of phases can you get in general for pair density wave states? Now on top of that, once you know what kind of ground states you can have, it'd also be interesting to know what kind of topological defects exists and how can they change the physics. And so the best way to do that is to construct a Ginzburg-Landau-Wilson theory for these. And I'm doing that here for a square lattice. And the reason I did it for a square lattice was because this applies both to the example of the cuprates and also to the cerium cobalt indium 5 that I really hadn't talked about. But in these two cases, you do have the point group is tetragonal, and so it's of relevance to consider a square symmetry. Right, so this slide is a little bit complicated, but the point is that when you want to describe the order parameter for such a pair density wave state, you have to consider, you have to assign Q vectors, of course, but then because you have square symmetry, if I take the Q vector here along the diagonal, then I have 4 Q vectors that are related by symmetry, and that tells me that the order parameter in this case is described by 4 complex degrees of freedom. So if I want to write down a general free energy, I need 4 complex degrees of freedom to do this, and then that's the main point you should get from this slide here. It's possible, and I'll make one other point here, to properly classify the states, you have to choose the Q vector and the equivalent Q vectors, which are called the star of Q, but then you also have to look at the representations formed by the point group that keeps a particular Q vector invariant. And the only thing I want to point out here is that this group, which keeps a particular Q vector invariant, does not contain inversion symmetry, as you might expect, because Q and Q1 and Q3 here are related by inversion. And because it does not contain inversion symmetry, this guarantees that whenever you have such a pair density wave state, you're going to get a mixture of spin singlet and spin triplet order parameters, or conversely, a mixture of S-wave and P-wave type order parameters. So this tells you actually that even the FFLO phase that you consider more generally must have this must have this odd parity contribution as well as the even parity contribution. So it's interesting to consider not just singlet interactions, the usual singlet interactions, but it's also interesting to consider the possible P-wave interactions in these, because it must admix. That's what this analysis tells you. All right. So I might come back to that later if there's time, where we did an analysis of the FFLO phase with this possibility in mind. But for now, just remember that there must be 4 complex degrees of freedom to describe the Ginzburg-Landau-Wilson theory for this order parameter.
Excuse me, do you have this result without spin-orbit coupling with by hand? So when you were saying that the S-wave and P-wave mix up, you don't even need spin-orbit coupling?
You don't need spin-orbit coupling. You can just introduce a, in fact, this is recently what we did. We added an S-wave and a triplet part. I may get back to this later, but what you can show is that you must always induce the triplet part, and there's Lifshitz invariants that guarantee that it shows up. And on top of that, it really does significantly enhance the stability of these FFLO phases.
I just saw that there are one-dimensional representation and two-dimensional representation of the square lattice symmetry group, and there was well, one-dimensional representation we'll call it basically S-wave, and there's P-wave, and there's nothing else, right? So there's no, well, there was a paper of Gorkov and Miniev which classified pairing states and the cuprates, for example. And, well,
but here I'm talking about the finite momentum, so it's spatially oscillating. And the spatial oscillations change the symmetry analysis. And so the symmetry analysis is what's here, right on the previous slide. That tells you these are the representations of this point group and then these are the possible singlet and triplet order parameters, and they must add mix because they're both the same symmetry. Yeah, so it just changes because you have finite momentum. All right, so I'm not going to go through the details, but you can construct this Ginzburg-Landau-Wilson free energy functional, and the first thing you want to look at is the mean field ground states. And so here I've just written out again the total order parameter in a simplified way. This is the total order parameter here with 4 components, qx minus qx, qy minus qy. And then you have to figure out the nonlinear terms in this function will tell you what linear combinations of these you can have. And so it turns out, for this particular case, it's possible to find all the homogeneous ground states. Homogeneous means that these order parameters are spatially uniform, but your total order parameter still has these spatial variations included. And I give all those here, and you'll see that there's a series of phase factors, and this actually relates to the Goldstone modes of the these types of orders that we were talking about, that Vincent Liu was asked about yesterday. You can show that this Ginzburg-Landau-Wilson functional has a U1 cross U1 cross U1 symmetry, and so that means that you either have 2 or 3 Goldstone modes showing up in these phases. And in fact, these phases tell you what the Goldstone modes are, because these phases are undetermined by the total free energy. And so here you see this phase in particular is very much like the phase that Vincent Liu talked about, and here you see there are actually three phase variables that are undetermined by the free energy. So these will be the Goldstone modes for the period. All right, so what are the kind of phases that you have? Well, there are 5 possibilities that are symmetry distinct. The first is the usual Fuller-Ferrel phase that we've all heard about. The second is this Larkin and Chinnikov phase, which is also very popular. And there's a couple new phases. There's this interesting stripe phase, which has these 2 plane waves here. And this has a lot of very novel features, but probably in practice isn't actually realized anywhere. This is a checkerboard phase, which people have seen in, have argued for in the context of D-wave superconductors. And then there's this vortex, anti-vortex lattice phase, where the order parameter has a series of point nodes in 2 dimensions. And around each of these nodes, the phase winding is either plus 2 pi or minus 2 pi. And it has a structure very similar to an antiferromagnet, but with orbital currents. Right, and this phase also has a broken time reversal symmetry in it as well. These other phases don't break time reversal symmetry.
So are all these phases stable?
I mean, so we do general symmetry analysis, and so we have a series of nonlinear terms, and then for a variety of these nonlinear terms, each of these phases are individually stable. So these are all the possible stable states you
So
can
there are regions of parameters where each of these phases can exist.
Exactly.
So actually, sorry, the 2 columns, right, left and right. So there's one-to-one correspondence.
Yeah, these are just renaming them.
Okay.
Fuller-Ferrel, Larkin and Chinnikov, and then vortex. They're just describing the order parameter on the left-hand side.
And the 3 U1 symmetries. So the first one is due to the particle conservation, I guess. Right?
Yeah, that's right.
Second
That's
one,
always there.
The second one and third one are due to the translation?
Yeah. So in this particular phase here, which is the most relevant to you, these are phonon modes along the x and y directions.
Mhm.
And they're exactly that.
So the rotation does not give you anything?
Here I fixed the
Like
Q
spatial
vectors,
rotation.
and I've imagined a true strict tetragonal lattice. And so I'm not imagining rotation invariant systems. And so the rotations can give you more, but it's not included here.
Mhm.
Yeah, and so one other comment I want to make, which is relevant for what's coming later on, is that along with each of these phases, you can always induce a charge density wave type order parameter, and that's just given by this particular combination of 2 Q vectors. So here I have minus Qi and then Qj complex conjugate. This structure is gauge invariant, and so it's allowed to be a charge order parameter. And then the plus sign tells you that it's even under time reversal, and so it has all the same symmetry properties as a charge order parameter. And so here I've written for general Qi minus Qj, but what's really relevant for later on is Larkin and Chinnikov phase, which has 2 Qs plus and minus Q, and then you get charge density order at 2Q for that. So if the LO phase is ordered at Q, the charge density order is at 2Q. And we'll look at that in some detail when we're talking about the two-dimensional fluctuation physics. All right, so I made a comment on the last slide that the full free energy had this U1 cross U1 cross U1 symmetry, and you don't often have these condensed matter theories that have such high symmetries. And so what I wanted to convince you of was that in a simplified version for this Larkin-Achinnikov phase, that you do indeed have a U1 cross U1 symmetry. And so that's what the point of this slide here is, because this product of U1s, of course, is very important for understanding the low energy excitations as well as understanding the topological defects you have. And so it's important to be sure that you believe me that it exists, right? All right, so the first thing you can do is just simply write down the Ginzburg-Landau free energy because you know the symmetry operators. And then when you look at this, this is the usual expansion. There's two fourth order coefficients, and then there's a spatial varying term, and then there's your TC term. But you can see right away that this depends only on the magnitude of psi qx and the magnitude of psi minus qx all squared. So each of these terms only depend on the magnitudes. In particular, there's no term written which looks like psi qx, psi minus qx complex conjugate. And that would break your U1 cross U1 symmetry. So the Ginzburg-Landau free energy has this property, and you can ask, well, is it a general property, or is it perhaps the fact that I truncated this at fourth power? And so you can write down a general term in your free energy, and that's what I've written down here. Just imagine psi qx to the power n, psi qx complex conjugate to the power n, psi minus qx to the power p, and psi minus qx complex conjugate to the power k. And so this would be an n plus m plus p plus k order term in your expansion. And then you can just impose two symmetries. The first is gauge invariance. Gauge invariance, each of these order parameters take up the same factor, and that tells you that n minus m plus p minus k equals 0, and it's n minus m because of the complex conjugate here and complex conjugate here. And then on top of that, you can impose translational invariance. And if you look at this order parameter, a translation affects qx and minus qx in opposite directions, right? So if I take x to x plus t, I'll pick up a phase factor e to the iqt, and here I'll pick up a phase factor e to the minus iqt. And so that tells you that this component and this component transform oppositely under this gate translational invariance. And so imposing translational invariance on the system will imply then that n minus m minus p plus k equals 0. And so you just take the sum and difference of these two equations, you get that n must equal m and p must equal k. And so you find that if n equals m, you get the magnitude of this squared, and if p equals k, you get the magnitude of this squared. And so that tells you that any term in this expansion for the Ginzburg-Landau free energy must have this U1 plus U1 symmetry. And it also tells you that this symmetry comes from a combination of gauge invariance and translational invariance.
Daniel,
Yeah.
Like what you point, you rightly point out already, if you add a lot of term, you can break the second U1. But if I look back at the microscopic Hamiltonian,
Yeah.
where the system is on the lattice,
Yeah.
so you do not have the translational continuous
Yeah,
symmetry
okay.
to begin with, right?
That's right. So here I'm imagining something like here I'm imagining Q vectors incommensurate with respect to the underlying lattice. You can add commensurability, it will introduce new terms. In fact, then you get this becomes modulo some vector. So you have to add commensurate terms in there. And some cases that really dramatically changes your physics, other cases it doesn't so much. It just depends on particular what the commensurability is. All right, so yeah, so here I'm considering, like the Larkin-Achinnikov phase, that would be some incommensurate choice, right? There's no reason for Q to be fixed the underlying lattice. But then in cases where you're studying, in particular if you have staggered plus minus, then the commensurability plays a very strong role, and that actually changes the physics a lot. All right. So I showed you that these theories, or in this particular case, has this U1 cross U1 symmetry. And so because of that, we know that we're allowed phase windings in the Q order parameter and the minus Q order parameter. And so it makes sense to consider these phase windings. And so imagine putting n phase windings in the first component and then m phase windings in the second component. And so the most standard thing you can do is you can ask how much flux do these defects contain? All right, and so that's what I'm just going through here, the argument, to show you that. So you can call these NM vortices, and actually Igor knows this very well. This is the following argument. But you can imagine I'm gonna allow this component to have one phase winding, this component to have no phase winding. All right, so it's approximately spatially uniform, especially far away from the vortex core. It will be spatially uniform. All right, and then you can ask, what is the total current corresponding to such a state? And this is just your usual quantum mechanical current. Because the first component is winding, you have derivatives of the first component showing up, but the second component is approximately spatially constant, so you have no derivatives of that showing up. And then coupling to the vector potential, well, both components couple to the vector potential, so you have both components showing up here. I should point out, I'm considering a full Larkin-Chinnikov phase, so far away from the singularity, you have this cos QR spatial modulation, right? So both
Daniel,
components are equal.
You,
Yes.
you don't have anything analogous to the Josephson coupling, like psi 1, psi 2.
Yeah, this term's not allowed by translational symmetry. So yeah, that was the, yeah. You do truly have U1 cross U1 symmetry, and the Josephson coupling would explicitly break that. So that doesn't exist here. All right. So far away from the singularity, the total current is 0, and then you can do a line integral on a path far away from that. And then this picks up a factor 2 pi. But the important point is that both components contribute here to the vector potential part, as opposed to the standard vortex where only one component would contribute here. And then far away from the singularity, these two would have equal magnitude, and that tells you then that the flux contained is half the usual superconducting flux quantity. Right? In the usual case, you would have a factor of 1 here. In this particular case, you have 2 here, because you have 2 components. All right, so this 1,0 vortex contains half the superconducting flux quantum, and then you can ask, well, how do you get the usual vortex? And that's just a 1, 1. That's where n equals 1 and n equals 1. They both wind the same way. And these are, of course, like I said, Igor looked at this a while back as well, in a different U1 cross U1 theory, where you've got actually a fractional vortices, but we won't go into that here. All right, so in this case, you want to understand the origin of these half vortices, to understand where they come from, and then we want to understand what physics they can have. All right. So let's look at this in a little bit more detail. So here I have, again, my 2 components, Q and minus Q. Here's Q and minus Q. And now what I'm going to introduce is the usual phase field. And on top of that, I'm going to introduce a pair density displacement field. So I'm just going to let x go to x plus u, much like we do for standard elasticity theories in just standard elasticity, continuum elasticity, for example. Right. Now, I require then, so Q times U is one field and theta is the other field, and I'm going to call phi Q times U. Maybe that was a poor choice, but okay, for this label. But I require each of these to be single valued, and so that tells me that far away, the winding of these 2 fields must be quantized, winding of this plus or minus this must be quantized to n2 times pi. And right away you see the origin of the half vortex. You can see that the phase can wind by a half as long as you compensate by a half winding in the displacement field. And so in some sense, you're coupling a half a vortex to half a dislocation in this FFLO order parameter. And in fact, you can make, and so what's important here for later is that the individual FFLO order parameter, or this particular psi qx, is affected by both the phase field and the displacement field. And for reasons you'll see in the next couple slides, it's interesting to consider the possibility, to consider order parameters that don't depend on the phase field and an order parameter that don't depend on the displacement field. And you'll see why that's relevant later. And you can construct those. The first is the charge density wave order parameter. I told you what this was before. This is psi qx times psi minus qx complex conjugate plus its complex conjugate, but here I've chosen real order parameters, so that doesn't matter. And in particular, if you look at this, it depends on these 2 components, but only on the displacement field. So it only depends on this Q times U. It has no phase field showing up in this. Right? So this is an order parameter that only depends on the displacement field and does not depend on the phase field. And then you can actually look at when you introduce a half vortex, meaning that this has to wind, and you can look at the structure of this corresponding charge density order, and you see that in the charge density order you get an edge dislocation showing up. So here's your charge density modulations of the Larkin-Chinnikov phase. You introduce a phase winding in this component here, and then sure enough, you get an edge dislocation showing up. So that's showing you that this does indeed couple to the dislocations. So here's an order parameter that's independent of the phase field. You can also construct an order parameter that's independent of the displacement field, and that's this one here. And this is a charge 4e order parameter. It depends on psi qx times psi minus qx, and then with this combination, it depends on 2 times theta, where theta is the field phase, the phase field. So this is a charge 4 order parameter that's translationally invariant, and then this is a charge density wave order parameter, as we understand. Right. So what I want to turn to now is the role of these half vortices, in particular, Koslostallis type physics in 2 dimensions. Yes?
So you're going to talk about the energies of these objects?
Yeah, I'll talk about this. That's actually the critical part of the next couple slides, is just the energies of these. All right, so just in case people aren't so familiar, here's your usual Berezinski-Koslostallis description in the qualitative form. And so your free energy is governed by phase fluctuations, and that means that this is just a usual superfluid in particular. And so that depends on this phase order parameter as the gradient of phase squared. You introduce vortex solutions, and so you introduce n phase windings, and then you look at the gradient of that, and that goes as 1 over r. And so you put that in here, you get an integral of 1 over r dr. And so you find that the energy of the vortex goes as log r over a, where r is the system radius. All right, and then the usual argument is that, well, if you introduce a vortex, your entropy is the log of the number of configurations. You can place that anywhere in your 2-dimensional system, and so the entropy goes as minus kBt log r squared over a squared. And then you can find out that the free energy to create a vortex changes sign because you have the same log r showing up here. And so at the place they change sign, kBtc equals capital K pi n squared over 2, you find that you go from a phase where vortices or individual vortices are not free to a phase where vortices are free. And as you cross that phase transition below Tc, you find you have power law correlations in the superfluid order parameter, but above it you don't have power law correlations anymore. And so that's the usual argument behind the Koslostallis phase transition. But what's really important, as you pointed out, are the energies of the single vortices. All right, so now we're going to talk about these pair density wave phases. We're going to look in some detail at the energies of these and see what affects that, and see what kind of phases can show up. All right, so that's the next slide here. So the first thing is that in a true superconductor, you don't just have the phase energy, you have a vector potential. It's gauged. And what does that mean? Well, the vector potential can screen the phase, and because it can screen the phase, it decreases the energy of a single vortex, and so your vortex is no longer log r, but has a finite energy. So strictly speaking, in 2 dimensions, as you mentioned this morning, you always expect to have vortices existing, because they have finite energy, not log r energy. And so if you have a superconductor, you expect that vortices are everywhere, and so that the overall phase coherence is destroyed, but your dislocations still cost log r energy. And so the dislocations are expensive to create, and so you don't disorder those. And so you expect that the surviving phase is a charge density wave order parameter, and a superconducting order parameter does not survive. Now, that was the argument we presented in our original paper. But then, very recently, or not so recently, a year ago, Radzichowski and Vishwanath considered the analogous situation in cold atoms, where they pointed out that, well, in cold atoms, if you have cylindrical symmetry, so your Q vector is free to rotate, then there's a famous argument that goes back to de Gennes that says that these rotations in Q, in some sense, serve as an effective gauge potential for the dislocation field. Now, I've written this in a very not correctly, actually. This form is not correct exactly, but it makes the analogy between the superconducting case and the rotationally invariant superfluid case very clear. Now you can see what happens. The dislocations are now going to have finite energy, but because it's a superfluid, you find that vortices cost log r energy. And so what you expect in this case then is that your translational order is destroyed, but your phase order is still well maintained. And so what you expect in this case is this charge force superfluid to show up. And that's what they argue in this. They do a 3-dimensional argument as well. They don't just do it in 2 dimensions. They show that the Larkin-Chinnikov phase is generically stable. Right. And then very recently, this group here pointed out that in principle it is possible to have the charge for a superconducting state without rotational invariance. And what they did to come up with that argument is they in essence said that the penetration depth of the superconductor is so long that you can actually ignore the vector potential. And then you get two different stiffnesses, one for vortices, one for dislocations, and then depending on which stiffness is greater or not, you can have one phase or the other. And so you can see that there's a variety of interesting types of phases you get here. And then you can ask, well,
So, but
maybe...
your vortices still cost log sample size to create.
Yeah, so I guess if you look at
The
samples...
fractional vortex.
Sorry?
If I'm considering a fractional vortex.
Yeah, there's still, the dislocation part is still there.
Right, so strictly speaking, for an infinite system, you can't create a fractional vortex because the divergent logarithm.
Yeah, that's...
Right, so,
Yeah, that's right. I mean, there are situations which I'll come to. Well, so here, the fractional vortices are relevant because
right.
they tell you that the charge density wave order survives, right? Because you can't create the fractional vortices. So even though you can't create them individually, they still have some interesting physics.
How about pairs? I mean, they would cut off.
Yeah, you can have plus and minus pairs, and then the dislocation energy will be finite. So, right? Yeah, so that'd be exactly like BKT physics in that sense. All right. So this is for this LO phase, and you can ask, well, are there other interesting phases you can? Oops, I skipped ahead. Okay, this is maybe in a. Sorry, I thought I was going to do this later. All right. So this is actually coming back to your point. In a high magnetic field, you can imagine an LO phase with perhaps rotating or in a high magnetic field. Then it's possible for an Abercosa vortex to decay, and so just 1, 1 becomes 1, 0 plus 0, 1. And in fact, it's then possible to have a lattice of half vortices. And in fact, you can show that this phase is indeed, in mean field level, this phase is indeed stable in Fuller-Ferrell-Archimedes superconductors in a certain region. Sorry? Near HT2, yes, this is near HT2.
So is it stable or metastable? Does it have a lowest energy? Or
It has the lowest energy in this region, but not in the entire region necessarily. All I can show is in a certain region of the phase diagram it is stable. The rest I haven't checked.
So to have this splitting and high magnetic field, you don't use mixed gradient gaps, right? It just
Here, no. So this is not using mixed gradient terms, but yeah. So the mixed gradient terms, yeah.
It's purely from being near HC2.
It's purely from being near HT2, but you can still have. No, actually, those mixed gradient terms won't show up if you're near HT2, anywhere near HT2. But if you go below HT2, but what that does is it leads to a difference between the phase stiffness and the dislocation stiffness. Actually, that's what it leads to. So there's a way of generating that. Yeah, so once you have these lattice of half vortices, and now because they're only close together, you don't have to worry about the cost of the dislocation field, right, because it's bounded, then you find that the total screening current is proportional to the sum of these two squared, and the total screening current then therefore corresponds to a lattice of actually half quantum vortices. So something very easy to see in experiment. You can actually directly see that. You can do neutron scattering on vortex lattices to see this. Oh yeah, this is what I've already mentioned. Right. So that was the spin 1/2 case. And more recently, we've been asking the question, are there other exotic pair density wave phases? I mean, the Larkin-Chinnikov phase is the most relevant, but you can ask on a general level, are there other phases that might be very interesting? And it turns out that most of the cases correspond very closely to Larkin-Chinnikov phase. And so the essential different phases you show up are, in some sense, closely aligned with what you find in that case there, except in one particular case. And that's this triangular phase where you get these 3 Q modes here, and the sum of the 3 Qs is 0. So in this particular case here, your free energy Ginzburg-Landau-Wilson functional has a U1 cross U1 cross U1 symmetry, and you can show that this phase actually has stable 1/3 flux quantum vortices. And so then, in that particular case, you can write down an order parameter for which is translationally invariant, but at the same time has the lowest order uniform superconducting order parameter that's translationally invariant, and that corresponds to a charge 6 superfluid or superconductor. And so in principle, it's possible to have a charge 6 superfluid in this particular case here. All right. so I think I've gone over time, right?
That's not. No, we started actually 15 minutes late.
I'm coming up to an hour. All right, okay, well let me just go through this, this singlet triplet mixing in FFLO. So the general symmetry applied arguments that there must always be singlet triplet mixing in paired density wave phases. And so you can ask, well, what happens to singlet triplet mixing in the FFLO case? And here's the answer. You can do, again, solve the Eilenberger equations and then look at the self-consistent solutions of that. And you find that here's your usual kink in the spin singlet order parameter for the FFLO phase. So here it's minus, and here it's plus. And you find that the spin triplet contribution shows up right around the node of the S-wave order parameter. And so that you can find it numerically. And so it's interesting because it shows up at the node, it of course affects the low energy states of this FFLO phase. So a couple things it does. So here, this is not a result that we had, but a result that also had been found earlier by Shimahara. But if you add the triplet and triplet channel as well as the singlet channel, then you find that generically you increase the stability of the LO phase versus when you don't have any spin triplet part at all. All right, and so here it's slightly exaggerated. The ratio that the spin triplet TC is half of the spin singlet TC. You find that you get this very large LO region. In fact, you even get this tiny little region of the FF phase. And it's this tiny little region of the FF phase that always shows up no matter how small the triplet part is, even though it shrinks. This is what ensures actually the existence of this 1/2 vortex phase that I was mentioning before. So the triplet part enhances the LO phase significantly. And it also has, like I mentioned, an important part in the low energy physics. So here, I'm looking at the Andreev mid-gap states. So I'll tell you what I mean. This is the local density of states when you're looking right on top of the node of the S-wave order parameter. So just where you go through a kink. All right, so along that node. And then if you had no Zeeman field present, then your standard arguments would tell you that you would have a zero bias state or a zero energy, or a state, an Andreev bound state at zero energy for this. So without a Zeeman field, this thing would lie right at zero energy. When you add a Zeeman field, you shift this, shift it in opposite directions for different spin channels, and so the zero energy state shifts up to plus and minus the Zeeman fields. And so for the conventional LO phase, this is your low energy spectrum. You have these Andreev bound states that lie at some plus and minus energy. What the spin triplet part does is it takes these states and pushes them away from where they were before. And so it pushes them out and pushes them further away from zero energy. And so this is a way that the spin triplet contribution enhances the energy. It in some sense, gets rid of some of the low energy states by pushing these states out further away. Right. And so that provides an understanding of the microscopic reason for the large induced spin triplet part. And then finally, the last thing I want to say is that you can understand this singlet triplet mixing again through Lifshitz invariance. This is maybe a little bit, so I don't know if everyone will be familiar with this notation. But if you have a spin triplet order parameter, it's characterized typically by a D vector. And then the D vector, the vector components of this correspond to the spin, and it has momentum dependence because it has to be odd parity due to Pauli exclusion. And so when you expand it, you can describe it by an order parameter of this form, corresponding to the spin and to the spatial orbital degrees of freedom. And then if you have a spatially varying S-wave order parameter, you can then write down this term in your action that couples the magnetic field to spatial variations of the S-wave and to the spin triplet order parameter. And the reason you can do that is because this is odd parity and this is odd parity. And so the combination becomes even parity. And so from this then, you can see right away that if this is spatially varying, e to the IQy, then that implies that this must also be spatially varying. And in particular, if you put in this cos QY solution in here, you find that the spin triplet part is exactly given by the sine QY, telling you it peaks where the spin singlet part goes to zero. All right. And so the important point from this is that the existence of this Lifshitz invariance always guarantees that you're going to have this S-wave, P-wave mixing in these FFLO states. Right. So at that point, I'll stop and I'll put my conclusions up. Open up to questions.
So I just didn't look carefully. So when you spoke about 6E phase.
Yeah.
So did you have to go, so to obtain this phase, do you have to go to infinite penetration depth limit, or what was the order parameter?
Yeah, you do. So the order parameter was exactly this one here. So if you look at this cascade of phases in 2 dimensions, it's one of the stable phases there, and it's right next to the LO phase. I mean, generally you can imagine this, so you need some underlying hexagonal material or cylindrically symmetric material, and in principle this phase can be stabilized as long as you have a pair density wave state. And so then the important point is that it has 3 Q vectors, but not the corresponding opposite directions. Right, so this would be Q1, Q2, and Q3, and the order parameter in each of the directions would have the same magnitude. And once you have that, then you're guaranteed these 1/3 flex phases.
So if you could show me again the slide with all the parameter.
Yeah, so the important one is Q1 plus Q2 plus Q3 sum to 0.
So when you already this delta 6E,
Yeah.
there is a phase when only this combination of the fields has broken symmetry, right?
That's right, yes.
Yeah, and to get so essentially, I mean, just ask what the correspondence. So, so in principle, if you have finite penetration depths.
Yeah, then this phase won't be stable
Yeah.
with finite penetration. Exactly for the same reason it shouldn't be stable. But then you can imagine a case where the penetration depth is very large again, and then you could stabilize such a thing. Yeah, so this is really relevant for superfluids, if you can ever make such a case in the superfluid.
What is the order of the phase transitions between the different phases?
These different phases,
Yes.
these are all second order in this case here. If you go to 3 dimensions, they turn out to be first order.
So even the first one, when you go from uniform to 1D, is second
Yeah,
order?
it's second order in 2 dimensions. I mean, so
Is it an assumption or it's a result?
this is the result of the clean limit in weak coupling for an S-wave superconductor with cylindrical Fermi surface. That's the result. So if you add impurities, this will change actually.
What determines the Q, magnitude of Q?
The Zeeman field in this particular case. So, okay, Q is 0 here and then grows as you move down. And then in the end it's given by the splitting of the 2 Fermi surfaces in the Zeeman field.
What, but the phase transitions are changing the Qs, right? Or
The number of Qs.
the number.
The number of Qs. So you can just ask how many Qs are stable here, and then you can just look at the free energy as a function of the number of Qs, and you see that you get this cascade.
So it goes 1, 2, 3. I mean.
Yeah, well, 2, 3, 4, 6, etc.
So it's just strange because the uniform phase doesn't have any Q, and then you go into sort of a solid-like phase, which I would assume to have a first-order transition, this fluctuation-induced first-order transition.
Okay, so the theory for the LO phase is not exactly the same as the theory of a one-dimensional solid. And in fact, it turns out for reasons I can go into with you later, that the FF phase is more like the one-dimensional solid. And then you get, well actually then you just don't have any long-range order. So, okay, this assumes second-order phase transitions. Okay, this calculation doesn't assume second-order phase transitions, but including fluctuations assumes that costless Thales physics applies still, right? Which assumes in essence that you're not preempted by a first-order transition. So I think that answers.
Quick question. Is this the, because you're talking about the case with spin orbital coupling, this is the case without spin
This is
orbital.
without spin orbit coupling.
Just
yes.
make sure that.
Yeah, so that's-
How do they, you organize a little bit, so basically they just write down the general form, for the mean field theory, they just write down most general form, a order parameter, with different K, with a set of K,
We just
set
said
of
that, yeah,
vectors.
you can write down the general free energy for as many Qs as you want. Actually, the functional form of that is not terribly complicated. And then you have a series of coefficients, and then you can look at those coefficients,
But-
and then
But how do they, so There should be more possible forms, I mean, possible configurations of Qs. How do they do that? For example, the Q can have different magnitude. So it's like just like this case, Q1, Q2, Q3.
So okay.
Each one of them can have different magnitude when you do the variational calculation. Right? So,
Yeah,
but
I mean
eventually-
it's okay. It's not necessarily so easy a calculation, but you can determine Q quite easily. Actually, that's a separate. That's something you can do almost analytically. And once you know Q, you can see the magnitude of Q. Sorry, once you know the magnitude of Q, you can look at all the possible combinations. I mean, we can talk about this in more detail. I mean, it's not my calculation, so I don't know how much I want to defend it, but we can. I can show you the relevant results.